All right, so here's like part 2 of the video. Now that we sort of know why this equation that's on page 1090 works, that is how we get from like a line integral to some sort of just plain regular old integral over t, I want to walk you through a specific example. This is example 4a from page 1091 of the Stewart book. It's also like shockingly similar to, I think, number 4 on this web work. So here's the deal. We're going to integrate the vector field like y squared comma x over the curve c that's a straight line that goes from this point -5, -3 to this other point 0, 2. The very first thing that we need to do is write down parametric equations for c. And to do that, we're going to use this trick of parameterizing a line, where we can say that c is 1 minus t times the point slash vector that we start at, so -5, -3, plus t times the vector that we're supposed to end at, 0, 2. You can see that this is going to work properly because if t is 0, then we're going to let t go from 0 to 1, right? If t is 0, then this becomes 1, and we just get this point, and this becomes 0, and so that point dies. So we do start at the correct point, -5, -3. And then when t is 1, this becomes 0, so this part dies, and all we get is 1 times the point we want to end at, which is like exactly what we want. All right, so now let's push some symbols around and simplify this and figure out what it is. If we distribute this 1 minus t through, we're going to get -5 plus 5t, and then -3 plus 3t. And then if we distribute this t through, we got to get 0, 2t. Adding those together component-wise will give us like, how about 5t minus 5? I like that better than -5 plus 5t. And then let's see, this will be -3 plus 3t plus 2t ought to be 5t minus 3. And you can check that indeed, as t goes from 0 to 1, we will indeed start at this point that we're supposed to start at, and we're going to end at this point that we're supposed to end at. I'm going to erase some of this and free up some board space for the next step. Okay, so now that we know what c is in terms of like x and y in terms of t, we can actually do the substitution process that I was talking about in part 1. So this y squared is going to become, here's our y. So 5t minus 3 squared. And then dx is just x prime of t dt. X prime of t will be 5. So then we have 5 dt. All right. And then x is this right here, -5t minus 5. And then dy is just y prime of t dt, so that's going to be 5 dt as well. The derivative of this is also 5. Okay. And then our range of integration is from 0 to 1 because that's the range of t values that gets us from the desired starting point to the desired ending point. So we ought to have the integral from 0 to 1. I'm going to simplify a little bit here. In particular, I'm going to factor out a dt. And heck, why don't we factor out this 5 while we're at it? So 5t minus 3 squared, that was our y squared. We factored out this 5. And then 5t minus 5, that was our x. And then we just have dt. Now this is just a regular plain Jane Calc 1 integral. All we have to do is simplify this out a little bit, expand the square, collect like terms, blah, blah, blah. And then it's pretty straightforward to integrate from there. So I'll leave that to you. I believe the answer ends up being -6/5. You can check. Okay, I hope this makes more sense. I hope this helps. Let me know if you have any questions. Cheers. Just kidding, I checked. It's -5/6, not -6/5.